Have you ever wondered why electrical engineers talk about different kinds of power, like real power and reactive power, when ultimately we just want to deliver electricity? Apparent power is formed from real and reactive power through a vector combination, specifically following the principles of a right-angled triangle, where real power is the adjacent side, reactive power is the opposite side, and apparent power is the hypotenuse. This relationship arises because alternating current or AC circuits contain components that store and releases energy, such as inductors and capacitors, in addition to components that consume energy, like resistors. Real power, measured in watts, represents the actual power dissipated by resistive loads, performing useful work. Reactive power, measured in volt-amperes reactive, or VARS, is the power that oscillates between the source and the reactive loads, necessary to establish and maintain electric and magnetic fields but performing no network. The phase difference between voltage and current, introduced by these reactive components, dictates this interplay. To practically understand this, imagine you have a system with both motors and heaters. The heaters consume real power to produce heat, while the motors requiring reactive power to create their magnetic fields and operate. To determine the total electrical capacity your system needs, you cannot simply add the real power and reactive power arithmetically because they are fundamentally out of phase. Instead, you treat them as orthogonal components in a vector space. You can calculate apparent power, measured in volt-amperes, or VA, using the Pythagorean theorem. The square of apparent power equals the sum of the squares of real power and reactive power. This calculation tells you the total power the source must supply, considering both useful work and the energy oscillating in the system. Electrical engineers often refer to this as the power triangle, a crucial concept in a C-circuit analysis. It elegantly illustrates how real power and reactive power are quadrature components, meaning they are 90 degrees out of phase with each other. The cosine of the angle in this triangle is known as the power factor, a critical metric indicating how effectively electrical power is being used. A power factor closer to 1 signifies higher efficiency because a larger proportion of the apparent power is real power, leading to reduced energy losses and improved system performance. Understanding how apparent power is vectorially combined from real and reactive power is essential for designing and operating efficient electrical systems. It enables engineers to correctly size components, optimize power transmission, and implement power factor correction techniques to ensure that the delivered electricity performs its intended function effectively, without a necessary burden on the power source.